Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, and I am your host today. This show is sponsored by myceudepot.com. That's MYCEU Depot. That's DEPOT.com for all of your continuing education credits online, engineers, electricians, forklift drivers, whatever it may be. You can go there and get your continuing education online 100%, automatically submits it to your state and gets that out of the way. So all of the proceeds that come from my CEU Depot help sponsors the activities that we do here at Electrical Code Academy Incorporated. That is why I can offer you all of this free training, free podcasts, and everything like that. Okay. Anyway, today's episode, we are going to talk about motors a little bit. I'm not going to be really intense with it because I understand that a lot of people listen to this while they're driving in their car, and I don't want you to have an accident because I don't want you flipping through your code book while you're driving. We know there's people out there that might try it. So, hey, disclaimer, wait until you get home or wait until you get to the office or whatnot. So we're kind of just talk a little bit about the Article 430. A lot of times I create graphics to depict this type of thing, and of course we have videos on motors, sizing motors and circuits and things like that, the feeder protection and short circuit ground fault protection for the string of motors. And I'll probably refer to a set of motors, that means an overload and a ground fault short circuit device, as a string. Okay, it's easier for me to depict it in an audio as a string, kind of visually, a mental picture, if you will. So I know people hear string and they think I'm talking about a PV or something, but you get it. Okay, you're much brighter than that. If you're listening to this podcast, you're a bright individual, I know. So anyway, I wanted to give some quick tips on marking up your code book. First and foremost, as we talk about it, kind of a tip segment, and then talk about each one of them briefly, of the different ones that we're referring you to. So that kind of gives you that really quick 30,000 foot view of motors. We're not going to dig down deep in the weeds because obviously it is a podcast and I want you to listen and enjoy it. But I want to kind of give you some things to think about and to let sink in a little bit. So the first thing is, in your code book, you'll have what's called a figure 430.1. And this is in, if you're in the softbound edition of the NEC, the 2017 edition is what we're talking about. It should be on page 297 or thereabouts if they've made any added changes to the code or revisions or whatnot. But in the 2017, it should be on 297 if you're in the softbound edition. Now, we're not talking about the spiral or the 3-ring binder edition. I don't know what page it might be on. But it's on 297 for Article 430 in the 2017 softbound edition. And there's a little table in there. And if you're preparing for an exam, or if you're just an electrician in the field and you want to make sure that you get to things quickly, because time is money, we want to get things done, then I'm going to give you some marking tips. This is not unique to me. There's other people that do this, but I felt it was good to pass it on to try to kind of help you. Now, I used to do this in the front of the book before I saw an individual do this actually on this formula, on this figure, and I thought, man, that's great. Let's keep it where people will be. Now, disclaimer. You need to check with your testing if you're taking an exam whether or not they'll let you write in your code book. Most states will let you write it in permanent marker or permanent pen. You just can't write during the exam, but you need to check with your testing authority to do this or not. If you can't do it, you can't do it. But if you have an addition that you can practice with, then this kind of just helps that ballistic type of training, whereas you're just repetitively doing stuff in order to remember stuff, because most of the time we remember stuff by just doing it. That's why I tell people when they listen to podcasts or they watch videos that they should also be writing things down as I say it or as you follow it online, because there's something about listening it, seeing it, and then physically writing it that unlocks this thing about you being able to remember it. And I like to refer to it as ballistic training, but because you're hitting it from all angles, ballistically. And no, I'm not a military guy. I just kind of thought that was cool. It just helps you learn, and that's what we're all about, is trying to build this memory, because you're not going to remember everything. I have to refresh myself all the time because I get so invested in certain areas of the code that some areas of it I just every now and then I got to go back and refresh myself. It just is what it is. I can't remember everything. I'm getting older. My capacity for memory is getting weaker over the time. So at any rate, we're going to talk to you a little bit about using this figure in the code book to jot down some really important sections and give you some page numbers as well. And we'll talk about each one of these just really briefly to kind of give you an overview, because it is a podcast. You need to watch our motors video to get more in depth about it. But if you see, you're on page 297, you'll see this little figure here. Great little figure by NFPA to put it in here, or I guess should say whatever code panel that did this. And it labels everything out. What would be neat if the code would actually, somebody would submit it to actually put the code sections beside each one like they do in the very first one for motor feeder. That would be awesome. But I guess it's so broad that you really couldn't just put one code section. So I get it. But we are going to do one code section for each. And to try to help us get in the area we need to be at fairly quickly. If whether you're on a job site, you obviously have limited time. You got to get to work. If you're taking a test, I don't want to go fumbling through pages. The words all get mushed together when you're under the time crunch of an alarm ticking off or a timer ticking off. So, all right. So you'd be surprised how quickly an hour or 2 hours goes by when you're under the gun of an exam. You're like, really? So the first one is motor feeders. What you'll have is a margin to the left and the margin to the right of this figure. And I'm going to tell you what to put in the left margin, and I'm going to tell you what to put corresponding in the right margin. All right, in the left margin for motor feeders, you're going to put .24, because that's going to tell us how to size the feeder conductors to multiple motors. Okay, so this is typically where I have a feeder coming out from a panel, and I'm going to be tapping to go to multiple strings of motors. And again, I'm going to refer to these motor sets where you have an overload, you have a short circuit ground fault, and the actual motor. I'm going to refer to that as a string, each separate altogether component, because it's just easier for me to refer it that way. You can like it or you don't like it. I really don't care. That's what I'm going to do. So the first one, for example, if I'm sizing that, if you looked at .24, it will tell you that you take the FLC of the largest motor that's coming off of this feeder, and you take the largest motor's FLC, and you do that at 125%, and then you take the sum of all the other motors' FLC that are on the same group, and then you just simply add their FLC to the sum you got from the largest motor, okay, or the highest rated motor as FLC, and plus the additional 25% of that. Okay, so we basically just say, if the FLC for a certain motor was 40 amperes, it's 40 times 125%, plus the sum of all the other motors that are in the same group. Now, what does the same group mean? Well, let's say I have a phase A, a phase B, and a phase C running down. It's a three-phase 208. If I have motors that are of different voltages, maybe I have one that's 120 aspect of it, that's a 120 volt motor, but then I have one that's single phase, and I have a motor that's three-phase 208, but then right beside it I have a motor that is single-phase 208. All of them, feeder tapping this feeder that's coming into this wireway. Then we have three different voltages here, or three different scenarios here. Two different voltages, but three different scenarios. So you want to when you find the largest motor, or the highest rated motor, you look at the phase that's connected to, and then you look at all the other motors that are also connected to that phase. And when you do that, then you're going to take that becomes your group, if you will. So you take that largest and you find what other motors are also connected to that phase, and you take the FLC of those. Okay, now if all the motors were all the same, and they were all three-phase 208 or 480 or whatever it is, then that'd be pretty simple. You're going to take the FLC of the largest motor, and then you're going to take plus the 100 times 125% plus the sum of the other motor's FLC, and you just add them up together. Okay, and that's what you're going to do. Now, so and that's going to determine the size of conductor that you need to have for that feeder application. Now, that's the importance of understanding what the group means. So it's the other motors that are in that same group, and then that's how you kind of balance it out. All right, so anyway, if you need to know more on that, you need to watch our video where we talk about motors. Single phase, three phase, doesn't matter. The group concept stays the same. And we show you how to do all that. But in your code book, on the left side for motor feeders, you're going to write 0.24. Okay. And on the right side, you're going to write page 303. Now the next one is motor feeder short circuit and ground fault protection. On the left side, you're going to write next to that .62. Now, Section 62 of Article 430 is telling us that we're going to use the values that we derive in 430.52, okay, to come up with the size of the largest branch circuit, short circuit, ground fault protection for whatever motors we're dealing with. You might have three of them. The largest one of all, you take that, whatever that resulted into the type of protection device, you take its value, and then you add the sum of the others, FLCs, of the other motors that are on that same group again. And we just talked about how you do the grouping. Now, again, you watch our video if you don't understand the group concept, and it's very hard to depict it here in an audio. But the grouping really means the other motors that share the same leg or phase as whoever you determined was the largest motor. Okay? So you might have three motors where all three motors don't share all of phase A, but the largest motor does, and then another motor does. Well, since the largest motor is on phase A, then you're going to actually share that application. All right. And then of course, if you have three phase and you have that running through there, then you're just going to look at which phase garners you the largest motor plus the largest FLC of any motor that's in the same group. Okay, so that's kind of the group concept, and again, it's best I can depict it here on an audio podcast. All right, so anyway, that's what .62 is dealing with, and it might be an inverse time circuit breaker at 250% of the whatever the FLC is of the largest motor. Okay. And remember, you're not doing the 125 because that's conductors. We're doing device protection devices now. So it would be 250% in accordance with 430.52. And so once you establish that, and you do that for each motor's branch circuit, short circuit, ground fault protection. Once you do that, then you look at which one's the largest one. And you take that, and then again, you take the FLC of the largest motor that's in that same group. Whether it's group phase A, basically whatever it is. I'm not going to rehash that again. And then you go and you select your overcurrent device. And remember that when you're dealing with .62, you can't do the next size up like you can when you're dealing with .52 if any of the exceptions apply. Okay. In this case, you got to size down. So let's say you did all this and everything and it determined that you needed 118 amps device when they don't make one. But because of what it says in .62 for feeders, you have to go down. So then I would go down to the next available under 240.6a, and that would be 110. So I go down to 110 amp device, and now I'm compliant. Okay, you can't go up when you're dealing with the feeder protection. You got to go down. Okay. So anyway, on the left side you write .62. On the right you write down page 310 because that's going to get you where you need really quickly. Page 310. The next one is motor disconnection means, and remember, we're following this little figure that's on page 297, and we're making these little notes in there, provided that if you're taking the exam, you need to make sure that you can write notes with permanent pen in your code book. Some states might allow it, some might not. So I'm not telling you to do something, and you say, Paul, you told me to do it, but they didn't allow it. You need to check with your state, okay? I know that, for example, Texas allows it, Virginia allowed it. You just can't write things in your code book during the exam, okay? There's a difference. All right, so the next one is motor disconnection means. So anything that you need to know about a motor disconnection means, this is where you're going to be, and it is .102. So in the left side margin next to motor disconnection means you're going to write .102. And then on the right side, you're going to write page 314. Okay? Now, other thing I'll get you to jot down there in the middle where you see that little disconnection means symbol that's right in the middle of the figure. One of the things I like to get people to write is if you write down that and you write .102 down, There's also something that you can put in parentheses in there, and that is under 430.10a. Then it says the disconnection means for a motor circuits rated 1,000 volts nominal or less shall have an ampere rating not less than 115% of the full load current rating. So this is talking about the rating, okay, the disconnection means rating. And so I usually will tell people right there, put 115%. Just put it in parentheses right there next to the little symbol of the disconnect right there in the middle, like a switch thing. Okay, just to write that in there to remind you that it can't be that the disconnect for motor circuits that are rated 1,000 volts nominal or less, which is probably what you're mainly going to deal with, shall have an ampacity rating not less than 150% of the full load current rating. So that if you get a question on the actual disconnection means and its minimum rating of it, there you go. All right, so you write that down. And of course, dealing with motor disconnection means, obviously we have the applications in there within sight, within 50 feet, and sight. Okay, if it was around a corner, it was still within 50 feet, but you couldn't see it, then it's not within sight. This also applies to different things like controllers and whatnot. So that's for another episode where we talk about disconnection means for motors, and 430.102 kind of gets into more detail with that. But you just got to understand that if you have something to do on your exam or you're practicing for a test and it's talking about disconnection means, that's where you want to be, and it kind of gets you there quickly. All right. The next one we're looking at is called motor branch circuit, short circuit, and ground fault protection. Probably in motors, probably one of the most important tables you're going to run into, except, of course, to find the FLC back in 247, 248, 249, and 250. When it comes to the actual FLC of these motors, I mean, that's probably one of the key places you're going to be. But again, when you're sizing short circuit and ground fault protection, you're going to have to be familiar with 430.52. Especially even when you're doing the feeder protection, it's going to send you back to the requirements establishing the fact that you decided which type of ground fault short circuit protection was for each one of these motor strings in order to be able to use that value in order to be able to size your feeder protection, right? So, I mean, that's kind of important to know. So what you want to write down right next to this one is .52 to the left, obviously. And then on the right, you want to write page 308 because that's going to get you there quickly. If I go to page 308, that's going to put me right at that table. In exam, man, seconds count. Okay? All right, and again, that table, .52, we're probably all familiar with it. If you are not, pause this thing and go get familiar with it because you're going to need to know that, because whether you're dealing with an inverse time breaker, which is your standard circuit breaker, instantaneous trib, dual element, dealing with fuses, or non-time delayed fuses, you'll have a specific percentage of the FLC current that you're going to value here. And this is a maximum rating. Now, you do have exceptions. Typically, the exceptions for the next size up is okay for the strings of the motors, the single, but not when you're dealing with the feeder, as we talked about earlier. But remember, if you're in an exam, most of the time, exceptions don't apply unless they state they apply, so don't get confused with that. If you don't see anything about exceptions apply, then you can't go beyond whatever the value is that you get here. So if it's an inverse trip breaker and it's 40 amp, you go at 250% of it, you can't go next size up unless exceptions apply. You have to go to the next size down again here as well. Just remember that. Most of the time, in real world, the exception, especially exception 1, will apply. But in an exam, unless they tell you the exception applies, do not assume it. I know people get messed up with that. They say, well, it's not real world. An exam is not real world. Exam is just trying to test that you know how to maneuver through the code book. That's all it is. Okay, it's not to take the place of your hands-on. It's not the. It's just that it's that final level of saying, okay, at least he knows how to use the code book, or she knows how to use the code book. That's all it's doing. I see so many posts online that say master electricians are no more than just passing the exam and learning the code. That is not correct. It's all about your education, your training. We're going to give you credit for your hands-on or what lack you may have. We're going to give you credit for that, but you still got to pass an exam. There's got to be something, right? There's got to be some threshold, and that's what exams are all about. It's a threshold. So we're just showing that, well, you know what, worst case scenario is at least he knows how to use a code book. And that's about all we can do, right? We can't fix stupid, but all we can do is use the NEC to kind of mitigate stupid. And that's what we're doing here. Remember that the National Electrical Code is the minimally safest structure you can have. In other words, on a grading scale from A to F, C is the middle of the road. It's a passing grade. That's about what the NEC is. It's a C. Can I do things beyond this? Sure. Could I put disconnects in locations where the code wouldn't actually require it, but I just want to put one in it because I feel it's better? Sure, I can. You can do things that are over and above the code if you want. Just be careful you don't go too far. And sometimes people, like with grounding and bonding, they go too far and they think they're making things better, and they're actually making things worse when it comes to circulating currents and objectionable currents and blah, blah, blah. Okay, so anyway, you can do more, but we're looking at the minimally accepted standard, and that's what the NEC is all about. It's your C. It's your middle of the road. You're going to be theoretically and physically safe, because this is a safeguarding people, document. You're going to be okay, but could you do more? You probably could, but we're not going to make you do more. All right. Now, there's some inspectors out there who might make you do more, but they shouldn't make you do more. It's the minimum, bare minimum, my friends. So anyway, there you go. You got that table. Just remember, read the question carefully. This is a great place to trick people. Remember, exceptions don't apply unless they state it if you're on an exam. I've seen more than enough people come crying to me because they failed an exam. Okay? All right, so that's what you got there. The next one we're dealing with is the one right under that. It is the motor circuit conductors. And again, that's our general requirements to size the motor to handle its load and to apply that 125% to the motor. It's continuous duty. Of course, you have all these other aspects to be aware of if it's not. But the general is .22. So in the left, you put .22. And that gets you at least to the motor circuit conductors. And there are a lot of people that also write beside that. When they do that, is they will write .22a and things like that. But really, I'm just trying to get you in that area. And then on the right side, we'll put page 302. I shouldn't say 302. 302. Okay, that's the Virginia in me. So 302 is what you're going to use as your page reference. Just jot it down in there. It helps you get there really quickly. That way you only have to look at the bottom right corner of the page to get you to the page you need to be. Okay. The next one we look at is motor overload protection. Now in the left-hand column you put .32 because that's generally the area you're going to get started in when it comes to overloads. And on the right side you're going to put page 304. Now, something else that I like to write in there between where it says part 3 and the little square in the middle of the figure, I like to put an A and a C in there. I put parentheses A, and I do the little and symbol, and I go parentheses C. The reason I do this is because A is going to be your general application when it comes to overload, but if you get an exam question that says the maximum, for some reason it says maximum in there, then you can go to C. And the percentage values of FLA change, okay, depending on the condition, whether the service factor, the rate of rise, the motor rating, or things like that. So I put both of them in there. A is your general, C is your maximum, which is what you could go to. Read your question slowly. The other thing that I usually will write in there is I'll also put in there FLA, and then I'll put NP after it. And that's to remind you that for overload protection, you're using the nameplate ampacity value. You're not using the FLC that's in the back of the book under the tables, 240, 248, 249, 250, 247, whatever. You're not using those of Article 430. You're not using those. You're using actually what's on the nameplate. So the exam will have to supply you with the nameplate rating. Now, don't get confused because in the question, they might give it as FLC. FLA doesn't really appear under this. It's still FLC. It's a full load current, but it's based on the nameplate. Okay, and the reason we kind of know this is because if you look back at the beginning of the code, if you happen to have your code book handy, you'll notice that it says, let's see here. Let me find the language here. Yeah, okay, so if you really quickly were to jot and look at 430.6 A2, it says nameplate values, and it just kind of tells you separate motor overload protection shall be based on the motor's nameplate current rating. Okay, so a lot of times I tell people to highlight that, the term nameplate, and then sometimes I'll even tell them to write that down right there by the A and the C. I'll have them write 430.6 A2, just to kind of make sure they remember that you're not going to use the FLC. So in an exam, they're going to give you the FLA, but they might refer to it as the FLC. But since you didn't have to go to a table, you're going to use the values that they give you in the question, because they need to provide you with that value, because there's a distinct difference between what's on the FLC versus what's on the nameplate. Now, they might be the same, but usually there's a little bit less on the nameplate, maybe an amp or two less. Not always, but generally. So they will supply you with that. Okay, so just remember that when you're doing the exam. But dot 32 to the left and page 304 to the right. Okay, and just remember writing the A and C in there. Okay, and you might even put an S over the A for the standard, and you might put an M over the C for maximum. Whatever you feel helps you. Okay, or maybe minimum under A over A and MAX over C or whatever like that. Just keep that in mind. The concept of C is if it overloads won't hold under A, that you can go to C. So that is theoretically the maximum you could go to under that type of scenario. If the question automatically tells you that, and many times a question will say, well, the overloads won't hold, what is the maximum? And you dissected the question to know that you're dealing with the other set of percentages, and that would be the under the C for the 430.32. Okay. Now, for all the other ones, I really don't give you any others, because you can just go to those parts pretty quickly, and at least one of them gives you, for the secondary controller, secondary conductors, gives you the actual section .23, and so does the one for secondary resistor. So they kind of tell you where to go. So I don't give you anything. The only other one maybe is the thermal protection one, because it does have some values that might be different as far as percentages that you got to work with for the thermal protection. If you wanted to write something down on that, it would be page 305, but that would be 430.32A2, and that gives you thermal protection. And thermal protection is dealing with an integral part of the motor. Okay, so it's built in, it's part of it. It's designed to prevent overheating of the motor due to an overload or some condition where it wouldn't start, it doesn't damage the motor. Okay, and then basically at that point you're dealing with the ultimate trip current of the thermal protected motor. Okay, and you follow the manufacturer's instructions for those type of things. Okay, but you have percentages there to deal with. When we're talking exam, usually you don't deal with that. We're talking about separate overloads, and that's important, because a lot of the graphics I give you where we're talking about separate, that's what we're dealing with in dot 32, is we're dealing with separate overloads. Okay, and that's important to distinguish. All right, but you do have some other aspects in there, thermally protected, integral, and all that. So again, this is not an all-inclusive podcast. It would be 2, 3, 4 hours long. I'm not going to do that. So that's where you're at for there. Now, that's pretty much all I write. Okay, for that, when it comes to that. Now, there's some other notes that I do put on this page that I like to throw out to you. So you'll notice to the left of this figure on page 296, there's a blank space at the bottom under 427.57. There's a little space there. You never know when you get a question on an exam, for example, that wants to ask you how to calculate the RPMs of a motor. And they're going to give you the number of poles. They're going to give you, the hertz and all, and you got to know the formula. Well, a lot of times what I like to do is write little formulas in here. Again, making sure that you're allowed to write in your code book. Every state's different. Every testing authority is different. Usually if you write it in permanent, and as long as you're not writing it during the test time, you're okay. Check with your state. But usually I write this formula. So you have a parenthesis, and then you write the word hertz down. And then you do a times symbol, X. And then you do 120, and then you do another parenthesis. And then you put a division symbol, and then you put a little symbol for the number, the hashtag for the number, and then right next to it you go of poles, P-O-L-E-S. So basically it's hertz times 120. You solve that first because that's in the parentheses. And you take that value and you divide it by the number of poles of that motor, and it'll be in the question. Trust me, they've got to tell you this information in order to be able to determine what the RPMs are. So, for example, it was 400 hertz. It'd be 400 times 120. divided, and you take that value divided by the number of poles. So let's say it was I'm just going to throw one out there. Let's say it was 6 poles. I don't know why it would be, but let's just say it was. And it was 400 hertz for whatever reason. So you saw the parentheses first. 400 times 120 is 48,000. Then you take that and you divide it by the number of poles, and let's say it was 6 poles. It's 8,000, so it's at 8,000 RPMs. Okay? There you go. So that would be, you look at your question, and that's going to find you with the RPMs. Okay. The other thing that I like to write down in this little space right here is I like to write down a quick table to which one of the actual FLC tables for 430 are for. For example, single phase, I do a little 1 with a circle line through it for single phase, and it's table 247. And then when it comes to the 3-phase underneath it, a 3 and a circle through it, I write .250. That's dealing with that table. All right. Now, if you want to put pages beside it, although you should have a tab in your book for this. If you have tabs, great. But if you don't, then basically the single-phase one is located on page 321, and the 3-phase one is located on page 322. So you can kind of jot that down. So there's still space in there if you write nice and neat. And then I add some more things. Also, next thing I like to put in there is I'll put down what's called single motor tap, and then underneath it I'll put feeder motor tap. And when I'm dealing with taps, that would be if it's a branch circuit, for example, where I'm feeding a wireway and I'm going to be coming off of a branch circuit because I don't have any short circuit or ground fault protection. I just have a fuseless disconnect that's going to go to a motor that has an integrated protection, overload protection and everything in it. It's all integrated in. Then all I need is a disconnect. And if that's the case, it's still a branch circuit. It's a branch circuit tap. And you have the rules you got to follow for that. And so those rules are found in 430.53D. So that's why I'll write that down. Single motor taps, I'll write .53, and in parentheses I'll put a D. That kind of gets you going there. And then for the feeders motor taps, underneath it I'll write that. I'll put feeder motor taps, and then I'll put .28. And .28 is the rules that are telling you for how to do the feeder. Now, what's the difference? Well, the feeder is I'm actually running a set of conductors out to, let's say, a wireway, or some people refer to as a trough, or whatever it is. And now I'm tapping those conductors, and I'm now coming off, and I'm going into a piece of equipment that'll have ground fault and short circuit protection for that motor string. Now, since I've got a branch circuit protection right there, that's a feeder that's feeding that. And so this is a feeder tap, and I have to follow these rules. And they're very reminiscent of the feeder tap rules that you see in 240.21, but they're unique, and you have to follow them. So all I want to do here is give you a quick way to get to those areas if the question's dealing with feeder tap, if that's what it's about. Okay, and it's simply dealing with that conductor from the point where it taps the feeder to the supply side of that breaker or fuse or whatever it is that you determine the size for the short circuit or ground fault protection based on 430.52. Okay, so that's what you sign. That's that piece there. Okay, that's the tap. Okay, so you follow all those different rules, and of course, depending on how far it is, 25 feet, 10 feet, whatever, then you've got these different rules you got to follow. They're pretty self-explanatory, but I just wanted you to understand that. When you're dealing with the branch circuit or the single motor tap that maybe just has a fuse disconnect, you have to remember that tap is the entire run through that disconnection means all the way to the line side of that motor or whatever, the controller with the integrated overloads or whatever's in it. It's that whole length. And so that's how you measure the length for that branch circuit tap. And it's got limitations as well under 430.53D that you have to follow. So I'm just kind of throwing things out there in your head, making you remember it so that you can go back and look through the code book and kind of get a better comfortable feel, especially if you're getting ready to take an exam on and kind of painting a picture. The other thing I will throw out too is there's certain things you see on an exam sometimes that they will try to fool you. I don't guess we're trying to fool you, but we might give you something that's sizing the conductors, but we might throw something in there about the service factor. Remember that service factor is for the overload application. It has absolutely nothing to do with sizing the conductors or the feeder protection or the short circuit ground fault protection. That only has something to do when we're sizing overloads. For exam, that's what you want to keep in your mind. So I sometimes will make a little note at the top of the page, or even if there's room down at that bottom left box, that I will say service factor has nothing to do with the conductor size. That just kind of reminds us that when you see something about service factor in a conductor sizing question, they're just trying to throw you off a little bit. Okay, don't get thrown off. Okay, now hopefully you wouldn't anyway, but it's kind of how it is. The only other thing that I like to write on this page is there's a little gap up here between the 430.2 definitions of what a controller is and this list of all these parts here. There's a little space right there, and I usually will put an asterisk, and then I'll write duty cycle table, and then I'll put 430.22e on page 303. So that's dealing with the duty cycle. So continuous duty, it's fairly easy, but you have to remember that we might be dealing with a case where we have some intermittent duty applications and whatnot. And so that gets us to that table when you're dealing with a 5-minute rated motor, 15-minute rated motor. That's critical when you're dealing with 430.24, where all of those are continuous duty or other loads, but then you have an exception if one of those motors might be a short time, intermittent, periodic, or varying duties. Then you might need to go over here to this little table here and follow this exception for that. So I like to actually just throw that in there to kind of get people to think, well, unless they say something otherwise, it's continuous duty, unless they state something. For example, an elevator would not be continuous duty. So if you were to look at that table, for example, you'll see that most of the time, one of the examples for elevators, passenger elevators, is under intermittent duty, and you'll see some nameplate current rating percentages that you have to apply here, especially when you're sizing the different types of motors, maybe in a set of motors or a grouping of motors. Okay, that's pretty much all I'm going to give you for this episode. I just remembered that if it doesn't say something, for example, with overloads, if it doesn't say the maximum, then you're going to follow the rules that are under for separate overloads under 430.32A1, and that deals with either it's 125% or 150%, depending on based on what the service factor is or what the ambient temperature is, or all other motors. Then you actually have to round down when it comes even to your overloads, okay? Because it says not more than the percentage. When it says maximum, then you could go up to the option C, or I guess I should say subsection C, or however you say it. Then because you're allowed to modify that, for this application, and C allows you to go up to the 140 or even or 130%, but you still can't go above that. You have to kind of go down or find something down. Okay, the next size down, whatever overload it would be. Okay, so that's just kind of something to throw out there. I'm just kind of looking at the different things. Remember that the 430.52, you cannot round up unless exceptions apply. That's the short circuit ground fault protection. When you're sizing the feeder protection under 430.62, remember that you in no time can you size that protection by going up. You have to size down to the next lowest overcurrent device if one doesn't correspond for whatever your calculation was. Just remember that. Trying to think of anything else I can give you, just to give you some stuff. That's pretty much. Let me try to keep this one short. So guys, don't get intimidated by your exam. It's okay to fail an exam. Now I get it, if you live somewhere where you got to travel hours to get to it, it's a pain in the butt. But if you pass an exam or fail an exam, if you fail it, don't sweat it. Even me, if I take an exam and I fail it, somebody might go, oh my God, Paul failed an exam? Who cares? Now, I typically don't fail exams because I do this for a living, but there are certain states that I would love to get an opportunity to take their exam and fail it once or twice, just so I can see what's on their exam and better do my teaching. So that's the curse of being an educator. Sometimes we want to fail something on purpose so that I can get a better grasp of the questions that are going to be on an exam, because I don't have a good enough memory to remember most of the questions when I take it the first time. Is it about the money? Absolutely not. I'm trying to better understand what that state's doing with their testing. That's all. Am I advocating that for you? Absolutely not. I mean, you want to get your exam and get the business. I mean, you got to make money. I'm different. I don't work in the field anymore. I help people understand how to pass the exams. I can't replace the knowledge that you should be obtaining in the field. I can help you understand the NEC, which ultimately is going to make for a safer installation. Okay? I'm not here to say that I can install a motor circuit better than Johnny, who's been doing it every day for the last 30 years and is still doing it. I'm not saying that. I'm saying that it shouldn't be brain surgery. I learned how to do it years ago. Nothing's really changed. All I got to do is follow the rules, right? And the NEC tells me the safety protocol. All I got to do is connect the raceways and get the different devices, and it's not brain surgery. So we're not expecting you to lose your hands-on. What we're saying is the reason we're learning the code, one, is to save mistakes in the field, make a safer installation, and nobody gets paid to do an installation twice. So you can have the prettiest looking installation you want in the world, but if it's done wrong by the code, it might work, and you can get frustrated. But if it's not by the NEC, then it is wrong. It's the minimum safety standard. From an A to F scale, if you install it in accordance with the NEC, it's a good C, maybe even a C+. Okay? And the concept of that is within sight, 50 feet or within sight, I could go all the way out to 50 feet. Or what if I put it within sight at 40 feet? Okay, well, maybe that's a closer. Maybe that's a B+. Yeah, you know what I'm saying? You can do the bare minimums, or you can go a little more. Just don't go extreme. Grounding and bonding, people tend to go way overboard, and sometimes that can create a problem. Anyway, that's the concept of today's show. Hopefully you got something out of it. I wanted to keep it under 45 minutes because it is I just do long podcasts. I can't help it. It's just the way I am. I'm long-winded. For all of my haters out there, don't worry about it. You don't have to listen. For all those out there that love it, tune into our next one. God bless, and thanks for listening. My goal is to see that you become the best electrician that you can be. If I can help you in any little way, that's what I'm here for. That's why I answer my phones. That's why I answer my emails. All of you out there who send me the love every day, the emails, the texts. I just got one this morning from a guy who passed his exam first try, and he learned exclusively watching our free stuff. That's amazing, dude. Keep up the great work, and you're going to be a superstar. I have no doubt about it. No doubt about it. So, till next time, stay safe, folks. God bless. And again, thanks for listening. Visit our websites, masterthenec.com or electricalcodeacademy.com. Visit our Facebook page. Just search on Facebook or go to our website, and you'll see the links at the top. Listen to our Twitter. Share these things with everybody. Don't be selfish. Share these things with other people. You don't have to listen to the podcast all in one sitting either. Okay? If I'm really long-winded, which I am, and I know this, people say things about me. Look, I know all the things you say. I'm not disagreeing. Can I be an a-hole sometimes? Probably. Do I help a lot of people? I do. Can I sometimes be abrasive? Maybe. My wife will tell you that. But at the end of the day, I'm just trying to help. That's all. So God bless. Till next time, stay safe, everybody.